This is A2physics 5, May 05. This is question 2 and it's about magnetic fields. A single turn rectangular wire loop ABCD hangs from a sensitive balance. So up here it's hanging from some kind of balance which is registering a weight, so that its lower portion is in a region of uniform magnetic field. Now you can't really see that. Let's see if I've got a pencil here. Maybe I could shade it in a wee bit. So there's a kind of a square area, rectangular area there and round there, and you can maybe see it better now. I'll just shade it a wee bit. So there's a region of magnetic field there. You would have seen that properly on the real paper. So the bottom half of the coil is in a magnetic field. When a current passes through the loop in direction A, B, C, D, so there's a current passing through the loop, the balance reading gets less. Explain why the balance reading is less when there's a current in the loop in this direction than when there's not. Now that means that this magnetic field is producing a force on this and it's pushing it up. And when it pushes it up, then the reading up here on the balance itself gets less. So I'm going to put in an arrow here, put in a green arrow, just to show that the reading, that the coil is being forced up. Okay, explain why the balance reading is less when the current in the loop is in this direction than when there is no current. So ABCD has a magnetic field associated. Oh, sorry, you can't see this. Has a magnetic field associated with it. This interacts with the uniform magnetic field. This causes a force. Now, the force only acts on BC because AB isn't at right angles to the field, and so the force is acting on BC. So AB and DC aren't at right angles to the field. B is the only one that's at right angles to the field. So this causes a force on BC, which causes it to move up. Now really you would have got your 2 marks there for saying about the force and the direction of the force, and then for saying about the fact that the magnetic fields interact. That's your 2nd mark. The next question. The dimensions of the loop are AB is 150 millimeters, so I'll just mark that in. AB is 150 millimeters along there, and BC is 50 millimeters. 50 millimeters is along here. The initial reading of the balance is 50.057 grams. When the current in the loop is 2.8 amps, in the direction of ABCD, the balance reading actually decreases. So it says calculate the magnitude of the magnetic flux density of the field. So we're going to use the equation F equals BIL. Now you have to decide which length you're going to use, and the length you're going to use is a length which is at right angles to the field, which is BC. And that's why they give you 2 lengths, to make sure you understand that. So the length is 50 millimeters. We're looking for B. We do know F because first of all we know the difference in mass is equal to 50.057 minus 50.035. And that difference in mass, see if I've got an answer to that. I'll just do that in the calculator here very quickly. 50.057 minus 50.035. That's 0.022 grams. But you have to convert that into a weight. And so W equals mg, and it has to be in kilograms. So it's 9.81 multiplied by 0.022 by 10 to the minus 3. And so that's the force. So B is equal to F over IL. That actually comes out to be, oh, sorry about the page. That actually comes out to be 2.2 by 10 to the minus 4 newtons. Okay, so it's 2.2 by 10 to the minus 4 newtons, and that's divided by I, which is 2.8, and the length is 50 by 10 to the minus 3 metres. And that brings you out as 1.54 by 10 to the minus 3, or 1.54 milliteslas. State whether the magnetic field is directed into the page plane of the loop or out of the plane of the loop. In other words, into the page or out of the page. Record your answer by placing a tick in the appropriate box. Give your reasoning. So we'll have a wee look at this. You can see there that we know the force is up. So if you take your left hand, I'll scan out a wee bit for this maybe. There's your left hand, and that's F, B and I. So we know that the current is flowing from left to right, FBI, so that finger there is across the way. We know that the force is upwards, so you have to turn your hand around like this here because your thumb is a force, and therefore that means that the field is going into the page or into the plane of, I think they call it into the plane of the loop. So if I just go back here, the field is directed perpendicular into the plane of the loop is the right answer. And then the reason why, I'll scan in again a little bit, and the reason why is due to Fleming's left hand rule. I is from B to C, F is up, and therefore B is into page. Without making any other changes, the direction of the current is reversed, so it passes around the loop in the direction DCBA. What is the balance reading now? So the force this time is going to be down, and that means that the original reading, which is the 50.057, is going to increase by 0.022 grams. And that comes out to be 50.079 grams.